All right, everyone. Good evening. It's December 12th, and let's see. We are here. I guess it's finals week for everybody, probably the finals week as we kind of head towards the end here. So hopefully we'll spend some time tonight getting you prepared specifically with the gas laws. So I have a brand new computer. I'm on a completely new computer. My old one was a laptop computer. It was 5 years old, and now I have this system that I built myself from components that is pretty cool. I have three monitors, one, two, three, and so hopefully you can hear me and you can see me and it works well. See a lot of folks here. Say hi if you're here. I see Jelly Times here, Lola, Creek, Taylor. Taylor's here. Good to see you, Taylor. Random. All right, and Alessandra and Carlemi. Awesome. Well, welcome everybody. Let's see. So how is my voice and how is the way I look? Is it any different now that I have this awesome new computer, or is it just the same? So I'd be interested in hearing that. Hey, thank you, Ashton. Hey, Kubra's here. Happy trails. All right. Wow, lots of folks. Excellent. So why don't we get started here? Gosh, there's a whole bunch more folks than usual. How many people do we have here? 31? Cool. Hey, Annie. So let's do this. Let's go to, where are we at? Let's go over to this here. And this is what we're going to use tonight to kind of help us do this stuff here. The audio is really good. Thanks, Taylor. That's great to hear. All right. Everything's looking good. Thank you, Lola. Right. Better. Okay. Excellent. So we're going to use this app right up here, and I'll put the link in chat. Let me do that for you right now, just so you have this. This is really good if you're trying to learn the gas laws. So what it's going to let us do is think about gas laws, but think about them in the context of kinetic molecular theory and what is the particles doing and how's all that work out, how's pressure, volume, everything related. We can heat it up, really put some flame on it there, and make those molecules or atoms move quicker. So as we're doing this, the big thing I want you to think about is when particles are hitting the sides of the container, those collisions, that's what's causing the pressure. So whenever we're talking about pressure, we're talking about the atoms or the molecules hitting the side, and that's creating the pressure for us. So if you can think of it that way, that might help you kind of make the equations make sense, because otherwise they're just equations. And of course, if we heat it up, you can predict what the atoms will do, right? Oh, we blew the lid off. Okay, so they move quicker with more force as well. All right. So kinetic molecular theory, that pressure, that's caused by the particles hitting the walls of the container, and that's really important. All right. So when you're doing the gas laws, you need to make sure that you're always working in Kelvin. Sometimes you can get away with Celsius with the combined gas law, but for PV equals nRT, always use Kelvin, and I always use Kelvin for the combined gas law as well. So take a second, see if you can figure out what 20 degrees Celsius is as Kelvin. All right, lots of folks here. Alessandra's here. Excellent, excellent. So all you need to do is take that 20 degrees right here and just add it to 273. So you should end up with, what, 293.15 K? And we never write the degree symbol with the K. Some teachers just tell you to use 273. Either way is good. Yep, Lola's got it, Taylor's got it. Excellent, excellent. All right. So let's give this one a try. This is the combined gas law right here. And what's really nice about it is if you don't have temperature, for instance, this is Boyle's law. So if temperature is held constant, it doesn't change, you just end up with Boyle's law. Or if you hold volume constant, you get another one of the laws, and so on. So if you know this, you know Boyle's, Charles, Gay-Lussac's, all those laws in one. So give this a try here. The one thing I do want you to note, though, is the volume of the container that's constant. It doesn't change. So we just don't think about that. So set it up, see if you can do it. Marlon, you asked about polarity. The rule of thumb, how can you tell which bond is least polar? It's based on the difference in electronegativity. And actually, let me see if I can get this here for you guys. This would be good for you to have. I'll have to look it up and see if I can find it. I think it's in the description. There's a link to a bunch of the stuff that the videos that I've done on those topics there. All right, so for this right here, we've got pressure, and it's 760 millimeters of mercury. Sometimes you'll see stuff in millimeters of mercury. Sometimes you'll see it in atmospheres, sometimes in kilopascals. It doesn't really matter because everything should cancel out here. So we are looking for, what are we trying to find? The new pressure here, we don't know this. 300, 400K. So if you work this out and you solve for P2, I'm not going to drag you through all that. I end up with 1140 millimeters of mercury. And somewhere I've lost my chat and everything. Oh, it's back. There we go. So you should have ended up with 1140 millimeters of mercury. But here's the important thing. What really changed was the temperature. So the temperature went up. So let's go back to our app and see what that means when the temperature goes up for pressure when volume's held constant. And really, Fiction, yep, you got it, but make sure you got your units in. They would be millimeters of mercury. All right, so let's reset all of this here. And let's put these small ones in here. I like those better. They're lighter, they move around a lot more. So here's our pressure gauge. What's going to happen to our pressure when we increase the temperature? That's the question. So try to visualize that. What's going to happen? So if you watch the gauge, as we increase the temperature, the atoms or the molecules are moving around. The pressure goes way up. And that pressure is because they're hitting the sides of the container. That's the kinetic molecular theory we want to think about. And then we just blew the lid off. So now they're just escaping out into the atmosphere there. All right, so always try to visualize that when you're doing these problems here. Let's go back. I can watch this for a long time. I don't know why I find this so fascinating, but I can just watch them move around. Kind of relaxing. All right. So 1140 millimeters of mercury. It does go faster, like you're saying. So we increase the temperature. That increases the pressure. So you can visualize that when you're doing these problems. All right, so give this one a try here. We have a few more things. Just try to set it up, and then we'll go over it real quick. So you really can't convert millimeters of mercury to grams because one's pressure and then one's mass. You could convert millimeters of mercury to, say, atmospheres, or you could convert it to another pressure unit. And you just would need a conversion factor to do that. You just need to know what a certain amount equals so you could convert them. Kind of like converting from feet to inches. You need to know that 1 foot is 12 inches. All right. So let's set it up. Initial pressure. And whenever you see initial and final, you know you're using the combined gas law. So that's always going to be what you're using when you have initial and final. So we have 2 atmospheres. We have a volume of 3 liters. And sometimes volume will be in milliliters. For the combined gas law, as long as it's milliliters on both sides, it doesn't matter. 300K. And over here, we go to 400K. 2.0 liters, and then we would just solve for P2. So you have to do all the algebra for that. When I do this one, when I did it earlier, I ended up with 4 atmospheres. Should be 4.0 since we have that many significant digits there. So we could leave it at 4 atmospheres though. So does that even make sense? If the pressure, if we go from 3 to 2, we made it smaller. We decreased the volume and we increased the temperature. So let's look at that and see what that looks like. So let's clear this out. So you already know what happens when we increase the temperature. That's right, Lola. So if you had, like, say, milliliters on both sides, for the combined gas law, you don't have to worry about it. You can leave it as milliliters. Or if you had pressure in atmospheres, for instance. All right, so we know if we heat it up, the pressure should go up. More collisions. What happens if we decrease the volume, though? So I can decrease the volume here. Watch the pressure. This is the pressure right here. Decrease the volume. And again, it's that kinetic molecular theory. We have more collisions hitting the sides here. Actually, if this is our pressure gauge, it went way up. It's this collision here that would be making the gauge read in real life. But the pressure is felt all around the entire container. Is temperature directly related to pressure? So as the temperature goes up, does the pressure go up? Yeah, definitely. So it is a direct relationship. If the volume goes down, the pressure goes down as well. Yeah, so ATM to, you don't have to convert from ATM to milligrams with that combined gas law, because everything will cancel out for us essentially, and we're actually left with ATMs. I think you were talking about the one with millimeters of mercury. So since we had it here, it's what we have in our answer. Cool. So let's move over to Pivert. So my students call this PV equals nRT. It's the ideal gas law. They call it Pivert, which I kind of like. I don't know. It helps me remember it at least. So this is Pivert here. And when you're dealing with the ideal gas law, understand that there's really no ideal gas. It's a bunch of assumptions, but there are gases that are close, and a lot of the important gases like O2 and H2. So it's pretty close. Your answer is, if you have a lower pressure and higher temperatures, it works out pretty well. So we're going to do this with Pivert. Just understand that there really is no ideal gas. It's a model. It's a tool we use to think with. All right. So here's the trick with Pivert. I'm going to keep calling it Pivert. The temperature has to be in Kelvin. If you don't have the temperature in Kelvin, it won't work. Pressure, sometimes it's in ATM, sometimes it's in millimeters of mercury. If it's in ATM, when you have R, this is our R here. If pressure is in ATM, this is the R you use. If it's in something like kilopascals, I think it's kilopascals, you use this. So you have to look at the pressure to figure out which value of R you're going to use. Volume has to be in liters. So Pivert is kind of very particular about the units you put in there. And if you look at R, you can see that you have liters here. So this has to be in liters. And then you have Kelvin here and Kelvin here. So you have to use Kelvin in your equation. So just try to set this one up. You might try to answer it, and we'll talk about it a little bit there. So give it a try. Pivert. Oh, Alessandro, I should do Henry's Law. I don't have anything planned this evening. But if you think about those, kind of that kinetic molecular theory, all this stuff goes back to kinetic molecular theory and thinking about collisions against the wall causing pressure and so on. I should do something on Henry's Law. It's a good one. Yeah, and Carl, I really like the visuals. I learn much better when I can connect the equations to some other thing like motion or visuals. I think everybody learns better that way. All right, let's try this with Pivert. Whoops, that's not what I wanted to do. I want the equation back. There it is. So we do have pressures in atmospheres. So that means this is going to be the R we use, because we have atmospheres, that's the R we use. So pressure is 1.2 atm, but we have a bit of a problem because volume is in milliliters. We don't have milliliters here. So you could do it, you could say 500 milliliters. You could do that dimensional analysis stuff, or you could just remember you divide by 1,000. 500 milliliters, and we know there are 1,000 milliliters in 1 liter. So when you multiply, you end up with liters. So 0.5, and that's the moles. We're trying to find that. R, we have to use this one because we have ATM. I'm not going to write all the units out. Whoops. And temperature, did we get 25C? So now we've got to change that to Kelvin. 25 plus 273 plus 25. Yeah, so 298. So let me just clear some of this up here. I'm kind of a messy problem solver, I think, sometimes. So if you do all of the units here, you can see that when you do the math, the ATM, the liters, everything's going to cancel out except for the moles. And if you do all of that math, what did I end up with? 0.24. So A. Did anybody get A? Pie Boy got A. Wow. And Really Fiction, you are right there too. You would have been able to answer that correctly because of the 0.024. You're very close to that. Ralph and I have a ton of videos on stoichiometry, not so much the limiting reactance right now. I'm kind of working on that. And Meta, you got A. Am I rounding to 2 significant figures? Technically here, it looks like you could argue that this is only 1 significant figure. But yeah, this here counts as 2 significant figures. So yeah, I'm rounding to that. All right. And so someone asked about stoichiometry. If you just go to breslin.org, I'll type it in there, my website, I have a really good section on stoichiometry. It might help you. All right. So we're going to do this last one here. What time is it getting? A little bit later. Let's do one last one here. And this one is kind of tough. So I want you to read it, but this does come up on exams a lot. This is ones where teachers kind of like to trick you with it. Read it real quick and think about it. All right, and I'm going to drop this in the chat as well. This is, my new computer is kind of confusing me because I keep reaching different places and things aren't there. This is a list of all the topics I have a lot of good videos for on my website. So if you just go there, that should set you up. I think that would work, Pie Boy. I think that would work. So here's how we do it, right? We are given grams. So when you see this, you may think, oh, wow, grams, that's going to need to change to moles. But they're saying identify the gas. So we don't use the grams till the end because we can set this up. We have 1 atmosphere. And I'm not going to do the units right now just because it's going to take a long time to write it in. 1 atmosphere, 58.4 liters. we want to find moles, because if we know the moles and we have the grams, we can find the molar mass and just look it up on the periodic table. We have R, since we have atmospheres, that's that 0.0821. And then we have a temperature, right, which would be 275.5. So if you do all of this and solve for n equals, what does n equal? 2.58 moles. So you get to that and you're thinking, okay, we're pretty close here. But you have to remember that molar mass is grams per mole. So I'm going to move this all over here. So molar mass is grams per mole. I have 10.3 grams and 2.58 moles. So if I take and divide 10.3 grams by 2.58 moles, I end up with 3.99 grams per mole. And that's the molar mass. So which one of these here is going to match up with the molar mass we found from the problem? Hey, thank you, Kimsa. That's most appreciated. I see Meta, Isabella, you all are right on target with that, right? The closest one, that's going to be helium. So that's kind of a tricky question. That would have messed with me as a student. So let me just go over real quick how I did it, just so you can see this again. They said identify the gas, and that's what gave it away for me. Identify the gas meant I've got to find N, I've got to find moles. And then when I saw the grams, I figured I could find the moles, and then grams per mole would give you the molar mass, and I just look it up. It's kind of a trick question, not completely. I guess it's a two-step question, and that messes with students quite often. So that's what I got for you this evening. I'm kind of excited that my computer made it the whole way through and nothing too strange happened. It's a lot easier to stream on this computer because I can see everything. I think what I'll do is wish everybody a whole bunch of good luck, but not really luck, just good studying and preparing, and hopefully the questions you study for come up on your exam there this week. And then I'm just going to stick around here for another 4 or 5 minutes. And if you have questions, maybe I can direct you to some resources, help you along there. But thank you, everybody for joining me here tonight. And this is Dr. B. As always, thanks for watching. And good luck on those exams. All right, so if you have questions, go ahead and ask in the chat, and I'll try to see if I can find some solutions or some help for you. If you do have a chance, go try this app out. It'll really help you understand what's going on. You know, if you can do those things for gases on the final, you'll probably be in pretty good shape. But also, you want to understand the conceptual stuff, like if you decrease the volume, what happens to the pressure, and what's causing the pressure, the collisions there. But that's the basic stuff at the general chemistry level. You might see some Henry's law or some Dalton's law stuff too. But this is really kind of the core of what they do. Yeah, I do this every Tuesday. I think I'll keep doing this after exams if people find it useful. It's kind of nice. When I create all my YouTube content, it's kind of like you create a video and you publish it, and then you don't really have any that much interaction with folks. So this is kind of more like teaching, which is something I enjoy doing. So yeah, I think I'll continue on Tuesdays for a while here. So Lola, if you're talking about beta, gamma, and alpha, that's all going to be your nuclear chemistry. And you probably want to understand kind of the decay type stuff. And you'll want to probably understand half-lives. I don't have any content that I've created, but there's good stuff out there. Look at nuclear chemistry for alpha, beta, gamma rays. Wow, 100 on an AP exam, my boy. That's impressive because AP is not super easy. They'll put that last question we did on an AP exam. They like that stuff. So, Isabella, if you're using the combined gas law, P1 V1 equals P1 V1 over T1 equals P2 V2 over T2, is they do need to be in the same units. It doesn't matter what units they're in. But if you're using that combined gas law, you've got to have it in liters for that. And that's because your R, the value for R, that's in liters. So your R wouldn't work if you had it in another unit. Wow, Carlem, you have a finals on the 19th. I don't know, that seems late for me, but I guess, yeah. So I'll keep doing it until then at least. Jelly time, I don't, there's different ways to do the limiting reagent. I probably would do a separate calculation just if I was teaching it at first. But there's a few ways to approach that. It's interesting because I see on my screen, my control panel, that it says buffering every once in a while, and then my picture will speed up real fast for a while, and then it'll freeze. Everything's delayed too, which is kind of weird. All right. Any other questions I can help you out with here? Alessandra, when we're looking at the ideal gas law and the combined gas law, they're all based on the same assumptions of kinetic molecular theory. The difference is with the combined gas law, we're looking at proportionality. We're looking at ratios, usually between initial and final. With the ideal gas law, we're giving a set of conditions, and then we can find the other conditions based on that. If we have all of them except one, we can figure out the last one. That's kind of the way I would describe it, but conceptually they're the same thing. Particles banging into walls, speeding up with heat. All right, reality fiction. You're having your exam coming up too this Thursday. Nice, soon, very soon. I wish you the best on that. I have a few videos on molarity, Isabella. Let me see if I can just find one real quick. Oh, I actually do have a fairly good video on molarity. I'm going to drop that in the chat. So this is molarity. There's molarity. I have a video on electrolytes. I'm not sure if it's between strong and weak. Let me see if I can find that real quick here. I can't seem to find that. If you type in Dr. B electrolyte, you'll find some videos on individual substances, and that might help. All right, Carlema, we'll see you next Tuesday, I think, then. All right. Lola's exam is tomorrow. Well, you better get studying. Oh, my link isn't working. Let me click on it and see what happens. Oh. Let me copy this one here. All right. Okay. Now I have too many tabs open, so I'm getting confused. All right. Maybe this will help. Maybe this link will help here. That did just work, and this one did work in my stream, on my computer. Redox. If I just did a big series on redox, I spent a long time on redox. And I'll put the link in there for you. Yeah, so if you need to know redox, I'm pretty happy with this. I spent a lot of time on this. And there's lots and lots of practice. So the guides, you'll see, I'll bring it over here. All of these guides here. So if you click on the guide, say for writing half reactions, which really causes students trouble, there's some explanation. There's a video just about that. And then some examples, and then more examples for the complicate, lots of examples, tons of practice. So yeah, and then each practice thing has a video attached to it if you need that help along with the answer. So, oh, you know what? My screen's not even up. There we go. Yeah, so this guide, the redox guide has all this stuff for you in here. All right. Yeah, Zachariah, you can ask a lengthy question. I don't know how well I'll be able to answer it. You know, teachers like to give lengthy answers, right? All right, I'm going to stick around for about another 2 or 3 minutes, and then I think it's night here. It's almost 9 o'clock, so. So the big difference between ideal gas, first of all, there are no ideal gases, but there are some close things to them. I would just say when we talk about an ideal gas law, we're saying that the molecules, they don't occupy any space. Oh, that's my stream. You're seeing my stream stuff. So when we're talking about an ideal gas, we say that the atoms don't occupy any space, and we say they don't interact with each other. And because of that, that's not really how it works. So a real gas, they will occupy some space and they'll interact with each other. So that's what I would say for that there. It's interesting. I find it difficult to, sometimes I'm moving things to weird places on my screen and all that. This is going to take some learning to get used to having 3 monitors here. It's pretty cool though. I highly recommend it if you can get 3 monitors. Yeah, Lola, I have a real good guide on, actually, yeah, Fresno.org. If you just go to the front page of my website, there'll be a thing that says stoichiometry. And I spent a long time. I even had one of the researchers that's actually working on redefining the mole as the SI unit review my stuff. So a lot of real good content there. So that's a place to go, I think. Well, Zach, that sounds like a complicated problem. So you have moles. I'm not sure what they're asking in your question there, Zach. How many moles of a gas are present at the end? So, Zach, let me get back to that real quick. So what's the point of the ideal gas law? It's really close. And it's really close when it matters. For the gases that it matters for, they're the ones where we breathe and we mostly use. And it's pretty close. Like if you use the gas laws, say for an airbag in a car, they would give you an acceptable answer. So you would know how things would work. The gases would heat and expand. Or if you drove like a race car, and when you drive, the tires get hotter, so the air expands. The gas laws would predict that really well. They're just not perfect. And for some gases, like ammonia that's polar and kind of attracts itself, the ideal gas law isn't great. There are equations like the van der Waals equation and even other ones that correct for all that, though. So if you know the ideal gas law, you can move up to more complicated stuff. So Zach, what I would suggest is start out with the combined gas law there. You might have to use PV equals nRT as well. Send me an email at drb@breslin.org and I'll take a look at it. It's too late at night for my brain to function at that level. Here's my email. Send me an email. So if you're calling it CuBr, we're talking about copper bromide here. Copper's a transition metal. So if you just called it copper bromide, I wouldn't know if it was CuBr or CuBr2, because copper can be 2+ or 1+. It has variable, and this is 1- here. So because copper can be 2+ or 1+, you've got to tell me that it's copper 1. That tells me it's this one. If you said copper 2, it would be that formula there. Hey, Chris, if you search on Dr. B, intermolecular forces, you'll probably find a video on that. Let me see if I can find that real quick. How about enter Dr. B? Well, that's sad. None of my videos came up. How about NH3? Haha, there I am. 2 of my videos came up. So I'm just gonna stop, pause. Let me just copy this and I'll drop it in the thing. Where's share? All right, there you go. That's the intermolecular forces. That should help you. Hey, thank you, Carlemi. That's awesome. All right. Oh, sorry. It's interesting. There's a delay on things here too. So like when I'm saying something, you guys aren't hearing it for a little while. Anyway, so what do the formula for finding frequency mean? I don't really have much content on frequency. When you start getting into the light and things like that, and determining the variables. I don't know if you guys ever used ChemLibre. This is a really good website. It's called ChemLibre, and they have all kinds of good content here. And it's all like open, free stuff. So I would take a look at what they have right there, and that should get you started with that. And they do a good job with it, and they have a lot of practice stuff. So I like that. I've written some content for them in the past, and it's all, you know, freely available stuff. There's no paywalls or anything. All right, guys, I think I'm how to do balancing equations. Oh, you got to go to my balancing equation. This is my best video in terms of like views. BALANCING equations. Balancing equations, which is too bad that I don't come up for. It's an older video. How to balance equations in 5 easy steps. It's got 5 million views. It has 93,000 likes. It's kind of crazy. There it is. So after watching that, you'll be able to balance equations. I have no doubt. All right, folks. Well, I'm kind of tired out here, so I'm going to go call it an evening here. Thank you, everyone, for joining me, and I'll be back next Tuesday. Then it seems like some folks would benefit from that, and I always enjoy talking with everyone. So thank you very much. And I'm going to go ahead and I think I'm going to go to bed. Yeah. All right. Take care, everyone. Thank you, Lee. See you next Tuesday, 8:30 p.m. Eastern Standard Time.